In the standard model of cosmology, dark energy is treated as an independent bulk fluid that fills the volume of the universe. This assumption requires massive theoretical fine-tuning to explain why the measured density of this fluid is infinitesimally small compared to the predictions of quantum field theory. The Kaczynski momentum constraint in general relativity offers a different perspective. It suggests that the flow of geometric information is controlled by the boundary of a space rather than its interior volume. Under this constraint, macroscopic thermodynamic properties do not have to emerge from an internal fluid. They can act as a top-down geometric admissibility condition imposed directly by the outer boundary. By focusing on the boundary edge rather than the volume, the cosmological constant shifts from an arbitrary fluid into a rigid, calculable geometric necessity. Attributing thermodynamic properties to cosmic boundaries is already a cornerstone of modern gravitational physics. In the 1970s, Gibbons and Hawking demonstrated that a cosmological horizon inherently carries a temperature, establishing the horizon as a thermodynamic entity. Later research showed that the Friedmann equations, which govern how the universe expands, can be mathematically rewritten as a first-law thermodynamic relation on the apparent horizon. In a flat FRW geometry, this boundary is the present apparent horizon, which coincides with the present Hubble radius. Since the horizon already operates under strict thermodynamic laws, we can apply universal radiative limits to it to determine its macroscopic state. This determination begins with the bedrock of photon gas thermodynamics, the Bose-Einstein distribution. The total energy radiated by a thermal black body is determined by a specific mathematical integral first evaluated by Leonhard Euler. Evaluating this standard Bose integral produces an exact analytical value, pi to the fourth power divided by 15. When we apply this value to a spherical geometry and remove the quantum constants, we are left with a dimensionless pure number, pi cubed over 15. This resulting normalization is a universal mathematical ratio, entirely independent of the scale, composition, or specific model of the system. We can connect this analytical number to physical systems by introducing a dimensionless photospheric quantity called X. When we couple radiative output with gravitational retention at a surface boundary, the variables for mass and gravitational coupling cancel out identically. The theoretical sharp boundary limit for this quantity is exactly pi cubed over 15, or approximately 2.0671. Observations of 190 detached eclipsing binary stars show no systematic dependence on mass across 2 decades of stellar parameters. The sample clusters tightly below the mathematical ceiling, with a mean of 2.0600. Our own sun follows this pattern at 2.0599, sitting slightly below the ceiling because its decoupling layer has a finite thickness. These results indicate that pi cubed over 15 is an empirically supported mass-independent geometric upper bound for spherical radiative boundaries. The core assumption of this framework is to apply this exact stellar limit to the apparent cosmological horizon. The dimensional scaling supports this. In photon gas thermodynamics, scale independence is only obtained in exactly 3 spatial dimensions. This yields a parameter-free relation. The cosmological term, lambda 0, multiplied by the horizon radius squared, is equal to the radiative normalization, pi cubed over 15. Constrained by its analytical origin, its strict spherical geometry, and the boundary's established thermodynamic status. By treating the universe's horizon as a boundary reaching radiative saturation, the cosmological term becomes a geometric requirement rather than a speculative fluid. This boundary condition immediately determines the present vacuum density fraction. In a flat universe, this yields exactly pi cubed over 45, or 0.6890. In a spatially flat background, the complementary matter fraction is therefore 0.3110. These derived fractions match the measured Planck 2018 parameters without requiring any free tuning parameters or adjustable inputs. This line graph shows the effective background trajectory derived from these partitions. It predicts the onset of acceleration at a redshift of 0.6425, where the trajectory crosses the negative 1/3 threshold. This reframes the temporal coincidence of our era. The observation that h0 t0 is approximately 1 is no longer a matter of chance. It is the algebraic result of the apparent horizon reaching its geometric radiative limit. We can bridge this macroscopic boundary to microscopic information using the Bekenstein-Hawking framework, which counts the horizon area in Planck units. Substituting our new boundary relation into this standard area count links the global scale to the Planck scale. This produces a closure relation, where the gravitational constant, the cosmological constant, and the horizon count form a closed algebraic triad. This suggests that the macroscopic boundary geometry dictates the microscopic information capacity, rather than the reverse. Within this triad, the gravitational coupling and the cosmological term are no longer independent. They are rigidly tethered to the total information state of the horizon. This closure addresses the conventional vacuum hierarchy problem, the massive mismatch between quantum field theory predictions and cosmological data. This massive discrepancy fundamentally arises when the theoretical vacuum energy is mistakenly calculated as a three-dimensional bulk volumetric ratio. By substituting the new closure relation, that ratio resolves into the horizon area count. The mismatch is not a failure of quantum field theory, but a result of expressing the horizon's geometric information capacity as a volume rather than a boundary. Because this model contains no free parameters, it is explicitly falsifiable. If the present vacuum density fraction is robustly determined to lie outside the strict interval predicted by the derivation, the boundary assumption is ruled out. Future kinematic reconstructions from Euclid or DESI will provide the data to either confirm or refute the predicted trajectory. This framework suggests that the cosmological constant is a macroscopic boundary condition, a universal normalization encoded into the geometry of the horizon.